Hi, I'm Ryan Nixon, and I'm going to talk to you about Euler, his formula, and some identities that we can derive from his formula. Specifically, we're going to have the perspective from your vibrations class, but this is applicable to so many different areas of math and science. Euler is ubiquitous. He's in all kinds of different problems and areas of modern science. So first, let's talk about the real and imaginary complex plane. So what I've drawn here is a unit circle in my complex plane with my imaginary and real axes. And then I just have what I call a unit vector in this space. So when I say something has a real or imaginary component, I'm not saying that the component does or doesn't exist. It's just a convention. It's a convenience. It's a way of describing my complex vector. So if it has a real component, then that is the cosine component of its behavior. And if it has an imaginary component, that's the sine component. So when we think of harmonic motion and vibrations, we think of a combination of sine and cosines, and this is how we can represent it. So if r equals 1, in other words, if I do have a unit circle, and phi equals omega t, which is often how we define phase, then I can write my, my complex vector here as the addition of my real and imaginary term. So the imaginary term has this I, which is my imaginary number, and we'll talk more about that in a bit. So for Euler's formula, the whole point behind it is it helps us express this combination of cosine and sine functions in terms of exponentials. So the idea is that my complex vector, x of t here, can be written as an exponential. So a complex exponential in this case due to the imaginary number. So to prove this, I'm going to be using the Maclaurin series. The Maclaurin series is a Taylor series expanded about 0. It's used frequently to model complex equations as much simpler ones. This summation, of course, carries out to infinity, but most of the time we'll be dealing in your engineering classes with some of the lower order terms to make approximations. In this case, as we prove the Euler formula, we're going to be using the exact definitions. So this is kind of our roadmap, and I'll walk us through the derivation of each of these. I'm going to start by expanding e to the y, just through a Maclaurin series, and I'm going to substitute in y later. And then I'll do cosine and sine and substitute y in. I'll add the cosine and sine and show that it's identical to my exponential. Okay, so for e to the y, I'm going to bring back up this definition real quick. So for e to the y, what I need to do is evaluate the function at 0 first. So we know that e to the 0 is 1. Then the second component is the derivative of our function evaluated at 0 over 1 factorial. So for us, if I take the derivative of e to the y, evaluate at 0, I get, so the derivative of e to the y is just y e to the y through chain rule. You evaluate at 0 and you get y. Because of my x function, which is actually y in this case. So for the next part, And essentially every single time I have to take a derivative and evaluate it at 0, I'm getting the same result. So what happens is I just get y squared over 2 factorial plus y cubed over 3 factorial plus y to the 4th over 4 factorial, and so on and so forth. So if I were to sub in my y equals I omega t, and I'll just show that real quick, y squared would be I squared omega t squared, and we know that I is the square root of -1, so that means this is just negative omega t squared. And then I just carry this out because I'll need, well, I've shown at least to the 4th power here, so negative I omega t cubed, sorry, this should be the whole thing squared. Omega t cubed, y to the 4th equals omega t to the 4th. So now we see the switch in the sign. So here's negative, now it becomes positive because of another I term. And then y to the 5th would just go back to I omega t to the 5th, reflecting again that sign change. So if I plug this in to my Maclaurin series expansion for e to the y, I can get 1 plus I omega t minus omega t squared over 2 factorial minus I omega t cubed over 3 factorial plus omega t to the 4th 4 factorial, and so on and so forth for an infinite number of higher order terms. Okay, so now we've done the expansion for our exponential. Let's do our cosine and sine. So if I were to do cosine of y, the Maclaurin series expansion will end up being this. So every time we have our sine function evaluated at 0, it goes to 0. Every time the cosine function is evaluated at 0, we get 1, and therefore we have a term. So we're skipping powers. Oh, actually, and we get alternating signs as well because of the derivative of the sine function is negative cosine. Okay, so there's our Maclaurin series expansion for cosine, and for sine, we get something similar for the same reasons. And so on and so forth for an infinite number of higher order terms. So now for the cosine and sine, I'm actually going to plug in omega t, not I omega t. And so for the cosine function, we get, this is cosine omega t. We have 1 minus omega t squared over 2 factorial. This is just a direct substitution. Plus omega t to the 4th over 4 factorial minus omega t to the 6th over 6 factorial, and so on. and then sine omega t. I just plug in omega t. So I get omega t minus omega t cubed over 3 factorial plus omega t to the 5th over 5 factorial minus, and on and on. So finally, if I add cosine and sine together, where the sine is represented by my imaginary part, so therefore cosine of omega t plus I sine omega t. So I'm multiplying this entire series by I. When I add those together, I'll write it over here. So I have cosine omega t plus I sine omega t. And I get the 1 from the cosine plus I omega t from the sine. And then the next component, omega t squared over 2 factorial from the cosine. And then the I from the sine. And then I just go on and on and on. And what I can see is that these are the same. I've just proven that they're identically equal to each other out to an infinite number in the expansion. Okay, so I've shown how you can take the summation of cosine and sine functions and turn it into these complex exponentials or express them in exponentials. So what about if I want to take a cosine function or vice versa? I found that you could turn sine into exponentials, and I want to figure out how you could turn exponentials into sine. I want to be able to go both ways. So this is the other component of it. So now I want to say, okay, well, what if I wanted to express my cosine as the summation of my exponential functions? So I'm going to start by using 2 vectors. My first vector, this is a complex vector, and it has some magnitude, and this is simply my unit vector in complex space, my general unit vector in complex space. And I also have another way of expressing the same complex function, and that's just in terms of exponentials. So I said that cosine omega t plus I sine omega t is equal to e to the I omega t. So these are the same thing. And then I came up with another complex vector called x2, and this is the result if my x1 complex vector is moving through complex space as a function of time. If I were to simply run that vector backwards in time, replace t with negative t, then I get my new x2 vector. And I carried that through, subbing in for every t, negative t. So x2 is actually x1 rotating backwards. So with these 2 vectors, I can develop 2 of Euler's identities. So first, I'm going to add the 2 vectors together. So x1 is going to be a, I'm just pulling the a out in front, and that is cosine omega t plus cosine omega t plus I sine omega t minus I sine omega t. And this is my first definition, so let me put a square bracket. This is as the addition of the sine and cosine components for my complex vector. The other definition I used was with the exponentials. So a e I omega t plus e negative I omega t. So this is the summation of this part, and then on the other side of the equation, the summation of this part. Okay, so now what I want to do is, obviously, those cancel each other out, and I combine cosine, so I have 2 cosine omega t. The a's are on both sides of the equation, so those cross out as well. And then I have e I omega t plus e negative I omega t on the other side. Then simply solving for the cosine function, I get e I omega t plus e to the negative I omega t divided by 2. So now I can transform my cosine function into the summation of these complex exponentials. Now if I wanted to get the sine relation, all I need to do is subtract the 2 vectors. So if I take x1 minus x2, then I'll end up with 2a I sine omega t. And that's going to be equal to a e I omega t minus e to the negative I omega t. So I skipped that first step, but the subtraction is pretty straightforward. And so now, again, we see that a is on both sides. I divide by 2i, and I get the identity for sine as e to the I omega t minus e to the negative I omega t over 2i. So now, with this relation, I can turn cosines into exponentials. And with the earlier relation we developed, which is Euler's formula, I can express my complex function as, which originally was developed as simply the addition of a cosine component and a sine component due to its harmonic nature. Now I can express it as an exponential. So what does this really mean? This means that the harmonic motion that we've been thinking of in vibrations can actually be expressed in exponential notation and still satisfy our differential equation, which the solution is a combination of these sine and cosine functions. So they still satisfy the solution, except now we can express them in a different way that's easier for us to manipulate. So hopefully that will help you with dealing with sines, cosines, and complex space. And good luck in your class, and thank you for listening.